The focus of this video is going to be taking a look at the rate of reaction and how temperature can influence the rate of a chemical reaction. This video will also serve as the background information for part number 2 of the clock reaction lab exercise we're doing in class. We'll explain how temperature can influence the rate of a chemical reaction by utilizing collision theory. The idea of collision theory being that reacting particles have to bump or collide in order for a chemical reaction even to be possible. But again, according to collision theory, our reacting particles, using their motion or kinetic energy, they move and bump into each other, and the bumping of the particles is what allows for a reaction to take place. Now, in order for a reaction to occur, the collision of the reacting particles, or the bump that takes place between reacting particles, requires a certain minimum amount of kinetic energy. That minimum amount of kinetic energy in the collision is what's necessary to cause bonds to actually break in the reactant particles, so the reactant particles can begin to turn into product particles by the formation of new bonds after the reacting particle bonds have been broken. This minimum energy is something known as the energy of activation. The same quantity, the minimum energy to cause a reaction, sometimes it may also be seen to be referred to as the activation energy or even the threshold energy. Energy of activation, activation energy, threshold energy are all interchangeable and are synonymous with one another. The activation energy in a progress of reaction diagram is represented by the size of the hump. This represents the minimum amount of energy that the A's and B's require to get over the hump and turn into product molecules. That represents the minimum amount of energy, or the energy of activation, for the particles A and B to collide in order for them to have bonds break and new bonds form as they transition to product. Another type of graph to help explain how temperature influences rate of reaction is a graph known as a kinetic energy distribution curve. Our vertical axis is the number of reacting particles we have in our sample. The horizontal axis represents the kinetic energy of those particles. What the kinetic energy distribution curve represents is if we have a container with some reacting particles, say our A's and B's, it gives us the distribution of the kinetic energy of those particles. If we could take a peek inside our container and examine the A and B particles, what we'd find is that in our sample, some of the particles are moving rather slowly, kind of put, 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 moving around. That'd be reflected by a kinetic energy of particles that have very low kinetic energy. Also within the sample, we'd find some of the particles that are moving rather quickly, have a high amount of motion. That'd be reflected by some of the particles that have a fairly high kinetic energy. The majority of particles, though, would be reflected by what we have for our average kinetic energy. On our graph, that tells us we have the most number of particles with that particular kinetic energy. But in any sample of particles, we have the majority with our average. There's going to be a few particles moving slowly and a few moving rather fast, but overall the sample is reflected by the majority of the particles showing our average kinetic energy. Now, using our progress of reaction diagram, we can say, let's just say for sake of our example, that this energy of activation is 40 units of kinetic energy. That's the height or minimum amount of kinetic energy required for a successful collision to convert reactants into products. What that allows us to mark on our kinetic energy distribution curve is the location of our cutoff. At 40 units of kinetic energy, this would represent our energy of activation. What that tells us is only the particles that have energy above and beyond this cutoff point or this small fraction of our sample of particles in A's and B's, have sufficient energy to react. Let's examine now, if we change our temperature, how our diagrams will look different, and how this tells us how temperature will influence the rate of a chemical reaction. Let's start out first looking at if temperature of our sample of A's and B's is increased. Now first, let's take a look at our progress of reaction diagram. This particular diagram remains unchanged by changes in temperature. Our energy of activation won't get changed by a change in temperature. The height of our hump representing energy of activation remains unchanged. Where our reactants start and where our products finish remains unchanged by altering the temperature of our reaction. Now, if we increase the temperature, what's going to happen is our particles are going to move faster. With the particles moving faster, what that means is therefore the kinetic energy average will increase. The average kinetic energy is a measure of the energy of motion of the particles. If the particles are moving faster from an increase in temperature, the average kinetic energy is going to increase. In our current diagram, the kinetic energy average is at right about 30 units of kinetic energy. Since our x-axis is kinetic energy, an increase in the average means that this peak or hump should shift over to the right to represent a kinetic energy of a higher value. With a new higher temperature, the kinetic energy curve is shifted to the right, and this is to reflect that the average is now at a higher overall kinetic energy for a higher temperature. Now the hump has decreased a little bit in height because the number of particles at the average energy is going to be slightly smaller. As we increase the temperature, the breadth or distribution of our overall kinetic energies gets spread out a little broader. Now a key implication of the curve, kinetic energy curve shifting to the right, is that now we have more particles beyond our energy of activation or cutoff, reflected by all the particles that would now be below the curve that are past the energy of activation. With a greater number of particles that have the minimum amount of energy to react, the reaction would proceed at a much greater rate under these conditions. On the flip side, if we take the temperature of our sample and decrease it, that's going to cause the particles to move slower. With the particles moving slower, therefore the kinetic energy average of the sample of particles is going to decrease. That would be reflected by a movement to the left of the peak of our curve, given that our axis here is representing kinetic energy. We'd shift to a lower value of kinetic energy for our average kinetic energy, or the height on our peak of our curve. At our new cooler temperature, see by the curve shifting to the left, our average kinetic energy has dropped to a lower amount. What this has done now is the number of particles past our cutoff right in here is very small, which would indicate that with so few particles having the minimum amount of energy to react, under these cooler temperature conditions, the reaction would proceed at a much slower rate.